In this class, we will discuss about the topic mutual induction. What is mutual induction that we need to define? Before that, let us consider two coils connected by means of or wound over a ferromagnetic material, a material which has high magnetic permeability. Now we are providing a varying current. A current is passed through this coil. A current is passed through the coil 1. As a result of passing this current through this coil 1, the coil gets magnetized, the core also gets magnetized. Which part of the core gets magnetized? Is it this much part or the complete core gets magnetized? I will tell you, the complete core gets magnetized in the process, which means that there will be a flexi linked with the second coil. So let us say the flexi linked with the second coil is directly proportional to current in the first coil, right? The flexi linked with the second coil is directly proportional to current in the first coil because magnetization of this core depends on the current in this coil, right? Because B is equal to mu 0 mu r and I. That is a formula for the magnetic field inside this core. So that means the flux linked to the second coil is directly proportional to the current in the first coil. Or I can say the flux phi 2 is equal to M into I1. It is M into I1 where M is called mutual induction. Mutual inductance or coefficient of mutual induction. Coefficient of mutual induction. So from here I can say the mutual induction M is equal to phi 2 divided by I1. Now just like self-inductance, the dimensions of we have to say that dimensionally it is same as self-inductance. So SI unit as well as the dimensional formula for mutual inductance is same as that of the self-inductance. So this is an important relation to follow. Now what is the EMF induced in the second coil? I can now differentiate this expression to get the answer d phi 2 by dt, which is equal to minus M into d I1 divided by dt. That is a formula for the EMF induced as a result of mutual induction. Okay. Now my question, how will you define mutual induction? How can we define mutual induction? Very simply, you can understand the definition. So what is happening there? So EMF is induced in the second coil, right? So we can define mutual induction as the process of inducing what? A current or EMF in a coil due to a change in current in the neighborhood coil. Change in current in the neighborhood coil. The process of inducing a current or EMF in a coil due to a change in current in the neighborhood coil. This is the definition of what I will say mutual induction. This is the definition of mutual induction, and this is an important formula to be noted as well. Now we will discuss about mutual inductance of a pair of coaxial coils. Consider two coils, coaxial coils, 1 and 2. So inner coil is 1 and the outer coil is 2. They have a common axis and both are supposed to have the same length. That is where self-induction can be defined properly. Now let us consider the situation. Let N1, N2 their respective number of turns, R1, R2 their respective radii of cross section. All such things we have to understand. Let us consider that the outer coil carries a current I2. When outer coil carries a current I2, I can say that the magnetic field associated with the outer coil is mu 0 N2 by L into I2. You have to understand that important assumption of a solenoid. The field inside is uniform whereas field outside is negligible. Mu 0 N2 I2 by L, right? I think there is no confusion in that. And the field due to the current in the outer coil is represented with this green color. I hope you can see it properly. This is the field inside this one, right? Now we are interested in the flux linked to the outer coil. Sorry, inner coil. Let us take that flux as phi1. The flux linked to the inner coil, I am saying phi1, which is equal to B2 into A1. That is a flux linked to 1 turn of the inner coil. That multiplied by N1, that is a number of turns of the inner coil. Okay. Now we will substitute these values. Mu 0, N1, N2, substituting here, we have N1 here, we have N2 here, divided by L into A1 multiplied by I2, that is a flux linked to the inner coil, that is a coil number 1. This is coil 1 and this is coil 2. Now what is the mutual inductance? If I write this as Mi2, as we have seen at the beginning of this session, this is Mi2, then my question, what is the value of mutual inductance M between the pair of coils? M is equal to what? You can see that this is mu 0, N1, N2 divided by L into the area of the inner coil, that is A1. This is also equal to mu 0, N1 by L is small n1, that is number of turns per unit length of the inner coil. Capital N2 can be written as small n2 into L into A1. Please understand, this is A1. This is the mutual inductance as a result of mutual inductance between inner and outer coils as a result of the fact that the outer coil carries a current I2. Now this is an important result you have to see. Now we cannot conclude as such right now because so this is the mutual inductance I said when outer coil carries a current I2. We need to prove that the answer would remain to be the same if the inner coil carries a current and the flux linked to the outer coil, when the mutual inductance of the outer coil comes out to be the same. So let us consider now the inner coil carries a current I1. Okay, without wasting my time, I can easily prove here. So keep a note of the assumption that the field inside a coil solenoid is uniform whereas field outside is negligible. Now this coil carries a current I1. Now as a result of this coil carrying a current I1, the field due to that one is linked only in the region inside that coil only, because field inside is uniform, field outside is negligible. Now what I can say, if B1 is the magnetic field produced by the current I1, I can say B1 is equal to mu 0 N1 by L into I1. Now we are looking at the flux linked to the second coil, which is B1 N2. Should I write A2? A2. The area where the flux is intercepted. You can see from figure. Where is the field located? Field is confined only in the region inside. There is no field outside, which means area. Okay, I'm telling you, please care of this point. This is A1, not A2, because area where the magnetic field is intersected is only A1. That's the reason. Now what is the answer we are going to get? Mu 0 N1 by L into I1. Now N2 into A1, right? So this is equal to M I1. So in this case, the mutual inductance M is equal to phi 2 by I1, right? Will there be any change in the answer? I think I'm getting the same answer, right? What I'm getting is the same answer alone, which implies what? The mutual inductance between. So this is an important question in the board exam point of view. Prove that mutual inductance of a pair of coaxial coils is a constant. So what I'm getting is M is equal to phi 2 by I1, which is equal to mu 0 N1 N2 divided by L into A1. The answer remains invariant here. The answer is not going to change here, so answer is a constant. Now the question generally comes, what if they have different lengths? I have to say, unfortunately, I don't know the answer. But experiments prove that the answer won't change appreciably. Experiments, I'm saying. So mutual inductance between a pair of coaxial coils is almost the same, on which length has only negligible effect is what? It is seen. So we will accept for this derivation, and this is the answer I have to say for mutual inductance of a pair of coaxial coils. We will consider mutual inductance of coaxial circular coils. Let us consider a circular coil of radius R1 and another circular coil of radius R2. From the figure you can see that R1 is much greater than R2. We provide a current I1 to the outer coil such that it will produce a magnetic field V1 is equal to mu 0 I1 divided by 2 R1 at the center. Since R2 is much smaller than R1, means with respect to this circle, this is a point-sized one, which implies the magnetic field is uniform over the cross-section over the area of the inner coil, that is over coil 2. Therefore, the flux linked to the second coil I can say B1A2. What is B1 is equals mu 0 I1 divided by 2 R1. A2 is pi R2 square. According to our knowledge, the mutual inductance M between the pair of the coil is equals phi 2 divided by I1, which is equal to what? Mu 0 divided by 2 R1 into pi R2 square. So this is the mutual inductance of a pair of coaxial circular coil or concentric circular coils, I have to say. The answer is mu 0 pi R2 square divided by 2 R1. Okay, now we are going to look at another situation. See here. So these are two coils. The self-inductance of this coil is L1. The self-inductance of the second coil is L2. This carries a current I. Now these two coils are carrying current in the same sense. Okay, this is a variable current. What is the total EMF in the first coil? This is the first question. What is the total EMF in the first coil? Now you can see that as a result of self-induction, there will be an EMF which is L1 into dI1 divided by dt. Now, since it is the same current passing through the second coil will create a mutual induction in the first coil, which may be written as minus M into di, or not I1, di by dt. Because it is the same current that is flowing through both the coils, and therefore the rate of change also must be the same. And similarly, what is the EMF induced in the second coil? Self-induction minus L2 into di by dt minus M. M is the mutual inductance between the pairs of between these two coils. M into di divided by dt. Now the effective EM of epsilon is equals epsilon 1 plus epsilon 2, which means I can take minus di by dt common factor. So I am getting the answer as, when you add these two expressions, di by dt is taken common factor, you will get L1 plus L2 plus 2M. Right? So this may be written as L effective into minus L effective into di by dt, and this will prove the answer as L effective is equal to L1 plus L2 plus 2M. This is the effective inductance between two coils if they carry current in the same sense. Okay, if the currents in the coil are in the same sense, currents in the same sense. Now tell me, what is your answer if the coils carry current in the opposite sense? Say one coil, this is the current is likewise. The other coil, the current may be in the opposite sense. So if I consider something like this, I don't say exactly. If you say the coil carry currents in the opposite sense, so here it is going into, in this case your answer has to be, I'm not going, okay, I will put plus here, I'll put plus here. So in this case it will become minus 2M. So effective inductance in this case is going to be L1 plus L2 minus 2M, because currents are in the opposite sense, I can say here, opposite sense, because here the current is going into, here the current will be coming out of the coil only. So that is where we say they are carrying currents in the opposite sense. So this is the effective inductance when the coils carry currents in the opposite sense, I have to say. Okay. A transformer is a device which works on the principle of mutual induction. A transformer is a device which works on the principle of mutual induction. What is a transformer? A transformer is a device that works on the principle of mutual induction. Basically, there are two types of transformers. One is called a step down transformer. The other category is called a step up transformer. Two types of transformers are, first one is step down transformer. Second type of transformer is called a step up transformer. Basically, a transformer consists of two types of windings. The first one is called the primary windings. The second type of windings is called secondary windings. Primary windings and secondary windings. So actually, whether the transformer is step up or step down, that is determined by the number of turns of the primary and secondary coil. Now let us consider the basic representation of a transformer. This is the figure that represents a transformer with the core of the transformer. Okay. Now before we start studying about a transformer, okay, transformer can be worked only with the AC. We cannot use a transformer with the DC. Please understand this point. A transformer is effective only with the AC, and you cannot use a transformer for DC. What is basically a transformer? A device used to step up or step down an input signal. Right, so now we will start discussing about transformer. So before we start the discussion of transformer, we will consider a few assumptions. We will consider a few assumptions. The first assumption is that there is no flux leakage in any part. There is no flux leakage in any part or flux per unit turn, in the bracket I say phi, flux per unit turn is a constant. The flux per unit turn is a constant. This is assumption number 1. The second assumption that we are considering is that the coils are ideal, which means resistance of the coils are negligible. Resistance of the coils are negligible. The coils are supposed to have negligible resistance. That is an important point you have to understand. The resistance of the coils are negligible. That means we are avoiding all chances of power loss, I have to say. The coils are having negligible resistance, you have to understand. So these are the two very important assumptions associated with a transformer. Important assumptions associated with a transformer. One is there is no flux leakage in any part of the circuit, or flux per unit turn is a constant. The second part is coils are ideal, that is the resistance of the coils are negligible. So keeping a view of these assumptions, let us consider Vp be the voltage applied to the primary coil. This is Ip, and the voltage induced here is epsilon P. And the voltage induced here is epsilon S, and the current here is Is, roughly showing the direction, because in AC the direction keeps on varying. Fine. And the output voltage across the secondary is say Vs. Now we have to say, applying Kirchhoff rules, total voltage is Vp. That is Ip Rp. Rp is the resistance of the primary coil, plus epsilon P, which is approximately equal to epsilon P. Why? Tell me what is the reason? It's approximately equal to epsilon P because I told you in the assumption that the resistance of the coils are negligible. And similarly, what? Vs is approximately equal to epsilon S. What is the reason? The resistance of the coils are negligible, right? That's the reason. Now, what is epsilon P? The voltage induced in this coil. I can say epsilon P, okay, flux linked to the primary coil. Phi P is equal to, what is phi? Flux linked to 110. Phi, what is phi? Phi is the flux linked to 110. I will say Np into phi. What is Np into phi? The flux of 110 is phi. There are Np turns in the primary coil. So what is the total flux? Simple mathematics. 110 phi. Np turns means total flux is flux linked to 110 multiplied by number of turns. So which means epsilon P is equal to minus d phi by dt. So this will prove out to be equal to minus Np, d phi p by dt, I'm sorry, minus Np into d phi by dt, right? Similarly, epsilon s is equal to minus ns into d phi by dt, because you know that phi s is equal to ns into phi, right? Ns means number of turns in the secondary coil. Now this is equation number 2. This is equation number 3. That means which is equation number 1? These are equation number 1, right? Using equations 1, 2 and 3, I can say that Vp by Vs is equal to Vp by Vs. Vp is equal to epsilon B. Vs is equal to epsilon S. So Vp by Vs is equal to, I can say, epsilon B is this much, epsilon S is this much, which will give you Np divided by Ns. This is an important ratio associated with a transformer. Vp by Vs is equal to Np by Ns. This is very, very important you have to understand regarding a transformer. The voltage in the primary coil divided by voltage in the secondary coil is equal to number of turns in the primary divided by number of turns in the secondary. This is one result we are considering. The next thing that I am saying is, for 100% efficient transformer, 100% efficient, that is where I said the assumptions. For 100% efficient transformer. What is it? For 100% efficient transformer, the power in the primary is equal to power in the secondary, right? That is what is said, 100% efficient. Efficiency 100% means whatever be the power got in input, that power will be completely transmitted to the output. Simple, easy logic. Whatever power in the primary will be transmitted completely to the secondary. So power of the primary coil is equal to the power of the secondary coil. So which means I will say VPIP. I hope there is no confusion in this discussion. Is equal to Vs into Is. Vs into Is. Now we can see that Vp by Vs is equal to S by IP, not IP by Is. Is, because I have taken Vs to the denominator. That is also equal to Np by Ns, as you can see here. Vp by Vs is equal to Is by Ip is equal to Np divided by Ns. So this ratio is called the transformation ratio of a transformer. Transformation ratio. The transformation ratio of a transformer is given by this equation. Now telling you, case 1, if Np greater than Ns, Np greater than Ns, Np greater than Ns, which implies Vp greater than Vs, or and Is greater than Ip. What kind of transformer is this? This is what is called a step down transformer. Step down transformer. So in a step down transformer, the voltage of the secondary is less than the voltage of primary. Can you suggest a place where a step down transformer comes into application? We have learned in the chapter current electricity that power transmission occurs at high voltage, so of the order of kilovolt. What is reaching to our home is just 230 volt or 220 volt. That means that 11 kilovolt transmission line, the voltage of 11 kilovolt in the transmission line is converted to 230 volt in our home, right? That means the transformers that you see near your houses or near your place is a step down transformer. There what is happening? The voltage is reduced, subsequently the current is increased. Now that is what done in the case of a step down transformer. Similarly, I am just taking here only case 2, if Np less than Ns. So in these cases what happens is, this is happening and this is what is called a step up transformer. And can you suggest a place where a step up transformer is used? We can simply say that in case of transmission to distant places, where a low voltage has to be converted into high voltage to minimize the power losses. So this is what is done in case of a step up transformer. Now before we wind up the chapter, actually this is a topic from the next chapter only, but since it is very close to what is the topic we dealt, that is the reason why I am taking it together. We will consider various losses associated with a transformer. Losses of transformer. The first loss that is associated with a transformer is flux leakage. Flux leakage. What do you mean by flux leakage? Okay, so we have assumed that the entire flux link of the primary coil is transmitted to the secondary coil, as I told you. But in practice, this 100% transfer won't take place. So which means there will be a loss of flux in the process, that is called a flux leakage. Second one is Joule's heating effect. Joule's heating effect. As I told in my assumption number 2, Actually, the coils are considered to be resistance free, but in practice, there is no coil which is absolutely resistance free in normal temperature. Otherwise, you have to take it into superconducting stage. That is practically impossible. So, all practical conductors you are using for coils must have some or other kind of resistance. I am saying non-inductive reactance that we will discuss in the next chapter. There will be resistance associated with the coil. So there must be energy loss as a result of the heating effect, which is given by I square RT. The heat produced is equal to I square RT. So there must be energy loss as heating effect. Then third loss we have to say is eddy currents. Eddy currents. So core of a transformer will have an iron core which will have some kind of area. As you can see in the textbook, this is maybe one construction where this is the core of the transformer. The primary coils are wound here. This is where the secondary coils wound. So this will be laminated. So eddy currents will be occurring in the core, which will also cause an eddy current losses, as we have learned as I square R loss with the core, not in the coil. So this can be minimized by laminating the core, as I told you on the other day. Like it is cut with a knife pointing in the direction of the magnetic field, and the cut pieces are again joined by an insulating adhesive. So this can be minimized by laminating the core. Eddy currents can be minimized by laminating the core. Okay, this is the third loss. Then fourth loss is energy loss due to electromagnetic radiations. Energy loss as a result of electromagnetic radiations. So accelerated charges would produce electromagnetic waves. So energy can be lost in the form of electromagnetic radiations. In addition to all these four losses, there is one more loss that is called hysteresis loss. Hysteresis, R-E-S-I-S, hysteresis loss. This loss arises due to the magnetization and demagnetization of the core. So these are the basic laws of a transformer. So in the previous video, I had a mistake. I just commit a mistake. Inside a cell, the current is from negative terminal to the positive terminal. In some part of the video, I said like it is from positive to negative. It's a mistake from my side. So while studying that, going through that video, so if you go through this video for one more time, please understand that the current inside a cell is from negative terminal to the positive terminal. I have drawn the arrow. I have put the polarities of the inductors in the correct sense, but in some part I said like it is from positive terminal to negative terminal inside a cell. No, inside a cell the current is from negative terminal to the positive terminal. Hope you understand this video, and that almost completes electromagnetic induction. Thank you.